Okay, so this is part 2 of our charged particles in an electric field, and we are going to look at kind of the trajectory of a charged particle in this second half of our introduction to this idea. And I just want to say, because chances are you're watching the second half right after the first half, because that makes sense. And there was a slight math problem in that last. It's in the description of the video, but somehow I added 16 plus 6 and got 23, and it should be 22. So obviously, when you look back at that video of our ion moving across the cell membrane, the force is not 10 to the minus 23, it's 10 to the minus 22. If you're stumbling upon part B and you don't know what I'm talking about, you can ignore that, or you can go check out that video and give you a little reminder of charged particles in electric fields. Magnetic fields. All right. The other thing I want to do in this mini lecture is introduce you to some visual that we represent. Now, we said that when we look at the forces exerted on a charged particle in a magnetic field, that it follows the right-hand rule. It's a cross-product behavior. And when that happens, we need to work in 3 spaces, 3 dimensions. So into the board, out of the board, and then in the plane of the board, or your paper or book or whatever. And so I do want to just remind you how we represent that 3rd dimension. So this pink X's here is our magnetic field. And this tells us that the magnetic field is going into the page. Okay, so the magnetic field is perpendicular to our plane, the plane that our charged particle is traveling on. It's into the page. So if we imagine those field lines as arrows, we see the tail of that arrow, the feathers. At X is into the page. If we wanted to look at something coming out of the page, we would represent that as a dot. So in this way, we can represent 3 dimensions in our 2-dimensional space. So I just want to remind you of that little tidbit. Okay, we know that because the field is perpendicular to the motion of the particle, that our charged particle is going to feel the maximum force, and it's going to feel a force perpendicular to its motion. So in this case, you just go ahead and use your right-hand rule. It's going to feel this force in the upward direction. So here's the force that charged particle feels at that point. So what happens if I have a particle moving to the right and it feels a force upward? Well, the trajectory of that particle is going to start to curve. Right? So it's kind of thinking, if you walk around and somebody pushes you, you kind of walk in a curved path, or you get deviated, and if they keep pushing you, you keep getting deviated. And so if we just take now, let's say we're at this location for this particle, and so now its velocity is in that orientation. Well, again, it's perpendicular, and it turns them a little more. So this should look familiar to maybe some stuff you did in Physics 1. As the force is perpendicular to the velocity vector, we end up with uniform circular motion. So as it continues to be perpendicular to that velocity vector, we end up with uniform circular motion, which means the particle feels a centripetal force, which we know is related to the centripetal acceleration, which of course is that speed over the radius. So we can describe the trajectory, the radius of that particle in using our ideas of uniform circular motion. If it's been a while since you looked at uniform circular motion and how that all works, go back and check out those videos on uniform circular motion to kind of refamiliarize yourself with this idea of centripetal force and the centripetal acceleration. Okay, let's use an example. Let's do an example that uses this idea. As I erase a little bit of this, we're going to talk about, I'll let you read, that's not the right one. Where is it? That's not the right one. That was the one from them before. There we go. We will look at an example of an electron, so a charged particle, moving perpendicular to a magnetic field. We're going to describe its trajectory by using the radius as our descriptor. So what is the radius of its motion, the radius of curvature of its motion as it enters this magnetic field. All right, so in this case, I'm going to draw it the other way just to give us some practice. So here we have the magnetic field coming out of the board, uniform magnetic field. We have our charged electron moving perpendicular to that field. What do we know then must be the case of the force this charged particle feels? Well, we just went through that. It has to feel a force perpendicular to its motion, and that's going to be in the downward direction. So use your right-hand rule to determine that force in the downward direction. We know that that force is equal to Q cross B. Therefore, the magnitude of that force is QVB times the sine of the angle. Put my little vectors on there. That angle being 90 degrees. So again, just to review, 90 degrees will give us the maximum force. So that's going to be Q times the speed, the magnitude of the velocity in this case, times the magnitude of our magnetic field. So this is the magnitude of the force. Now, because that force can be described as uniform circular motion, we know that that magnetic force, Newton's second law tells us it's the mass times the acceleration. We know it's uniform circular motion because of that perpendicular behavior. So we have the mass times the centripetal acceleration, which is the mass times v squared over the radius. So the magnitude of that force is related to its centripetal acceleration motion, and we end up with Q times V times B equal to M V squared over R. And I can solve for R, so R is equal to MV over Q times the magnetic field, and then we can plug in our numbers. So we know that the mass of an electron is a known quantity. The mass of an electron is 9.1 times 10 to the minus 31 kilograms. We're told that it travels at a speed of 1.6 times 10 to the 7th meters per second. The charge on an electron is also known, 1.6 times 10 to the minus 16, and we're in a 0.02 Tesla magnetic field. So solving for that, and we get our radius to be 4.6 times 10 to the minus 3 meters, or 4.6 millimeters. So that is the radius of the circle that this charged particle is going to feel as it travels through this magnetic field. All right, so using that idea of uniform circular motion, recognizing where that comes from, practicing a little bit with the forces charged particle feels in a magnetic field. All right, good job.